welcome to another AQA AS chemistry video. Today I'm going to be doing a video on polarity. So let's get straight into it. So polar bonds. So some bonds within molecules, which is intramolecular bonds, may be described as being polar, and this is caused by differences in electronegativity. So in a bond between two unlike atoms, one atom will have a stronger attraction to the electron pair than the other, meaning that the electron pair won't be at the center of the bond. So when I mean the electron pair, I mean the bonding pair. The electron pair in this case is the bonding pair, right? And usually between atoms, right? So if I say between a carbon-carbon bond, right? A carbon-carbon bond, right? Because it's the same atom, same electronegativity, the electrons are equally pulled between between each carbon. So the electron pair or the bonding pair in this case would be directly at the center of the bond. Whereas compared to a carbon bromide bond, because bromine is much more electronegative than carbon, the electrons are actually more closely attracted to the bromine than they are to the carbon. Alright, so this causes a buildup of partial charge on an atom, and this is written as a delta positive or delta negative. This is called the partial charge. When we write it as this lowercase delta, which is a lowercase delta, that represents partial charge, and you've probably seen this when it comes to electrophilic addition, right? But just to emphasize this previous point here, this is still true for like other cases. Like for example, let's say a carbon-hydrogen bond, right? A carbon-hydrogen bond is described as being very non-polar. The reason for that is because there's a very low difference in electronegativity. There's not a big difference, but technically carbon is slightly more electronegative than hydrogen, so the electron pairs are slightly more attracted to the carbon than the hydrogen, but overall there's a very small difference in electronegativity, so it's regarded as being pretty much at the center of the bond. So it's closer to being, the electrons are more close to being, you know, at the very center of the bond. But this is true for any case where there's two unlike atoms or two different atoms being bonded together. But yeah, so it's just to do this is more to do the difference in electronegativity. The larger the difference in electronegativity, the further away that electron is from being at the center of the bond. Alright, so but this partial charge, or the way you represent partial charges is by using this lowercase delta, right? So you may have seen this in electrophilic addition, right, where you see the alkene group here, and let's say hydrogen bromide, right? Right, that's partially positive, and then this being partially negative. It's just like this is more partially negative. It's more electronegative than the hydrogen, but it's not fully negative and not fully positive because it's still within that bond. All right, so now that's it. Now let's go on to the next part here, which is the definition. If there's anything I don't really encourage writing anything down for my videos because there's probably better videos out there. However, if there's anything you'd ever want to write down, this is it, and that's the definition of electronegativity. So this is a definition. They can ask you this in the exam. What is electronegativity? And it's the ability of an atom to attract the electron pair within a covalent bond. So the ability of an atom to attract a valence means is the electrons that would therefore react with another compound, but don't need to say this valence part. But it's the ability of an atom to attract an electron pair in a covalent bond. You have to say in a covalent bond, because everyone remembers the ability of an atom to attract the electron pair, but it's not the full definition. It's the ability of an atom to attract the electron pair in a covalent bond. Alright. So going to go on to the next part, which is Pauling's electronegativity. So what is Pauling's electronegativity? So this is a table, right? And this is actually designed by this is the electronegativity, right, of each atom. This is I mean, they have done the entire period. Is this the entire period? I think we're missing some. Yeah, the lanthanides. But it's generally the ones you need to know is about like these are different this is the electronegativity of each atom in the periodic table, at least the ones you need to know. Now in the exam, I don't want to overstress this because it doesn't come up as much in the exam. But I don't think it has to come up in the exam, but you just need to know of it just need to know what it is, and there's just a table that shows the electronegativity of each atom, right? The why is it called Pauling electronegativity? It's just designed by this guy, Linus Pauling, an American chemist. So the values of electronegativity can be measured on several different scales. The one to remember is the Pauling scale. As I said before, they might for some reason they want you to know what this is. I've never seen it in an exam, but just knowing what it is, maybe they might throw it in an exam one day, but I don't really think it will. But just understanding what it is important. It's not too difficult to understand. Right, so the values of electronegativity can be measured on several different scales. The one to remember is the Pauling scale. The most electronegative element is fluorine, which has a value of 4.0. Other strongly electronegative elements are oxygen, which has 3.4, chlorine 3.2, and nitrogen, which is 3.0. Carbon has an electronegativity of 2.5, and hydrogen has electronegativity of 2.2. So you can clearly see that, as I said before, carbon-hydrogen bonds, as I showed up above, they're not very electronegative, and it's because it's such a low difference in electronegativity. It's a very non-polar bond. If it was a carbon-fluorine bond, that's a massive difference in electronegativity. So that would be that would be considered the polar bond, because the difference of 1.5. This is 0.3. So it's not a very polar bond, right? But there is still a difference in electronegativity. Polarity. The most electronegative atom in a bond will develop a partial negative charge, and vice versa. So this charge difference is called the permanent dipole. So yeah, it's pretty self-explanatory. Really. The most negative have the most electronegative compound the most electronegative compound, so most electronegative atom in a covalent bond will be having the partial negative charge, and therefore if one is partially negative charged, the other one must be partially positively charged. For example, hydrogen chloride is a polar bond. A good example of a non-polar bond, as I said before, a carbon-hydrogen bond. Remember, high difference in hydrogen is 2.2. Was it before? Yeah, carbon is 2.2 and chlorine. So hydrogen is 2.2 and chlorine is 3.2. So difference of 1. So that's considered to be a polar bond. So the electronegativity of hydrogen and carbon are very similar. So the bond isn't polar. Polar molecules. Molecules can have an overall dipole, just like bonds. So molecular polarity. So molecules can be polar. A requirement for a molecule to be polar is that it has a polar bond. If there's a charge separation between one side of the molecule and the other, there'll be a permanent dipole. So a good example is chloroform, right? So let's get chloroform is CHCl3. CHCl3. This is known as chloroform. There's a permanent dipole because there's 3 polar bonds. There's a difference in polar bonds, and you can see there's a clear charge separation. It's not this part isn't that electronegative, so the bond's relatively here. But when it comes to these, because remember with chlorine you got 2 bonding pairs on either side, right? So you got 4 bonding pairs on all 4 sides of this carbon. However, because chlorine is so electronegative, they're pulling the bonds here or closer to that, and this is here. So there's a clear charge separation. This is considered to be a polar bond because this is in the middle, being pulled here, being pulled here, being pulled here. It's clear charge separation. It's not equally distributed. However, there's some finer details I want to go through. A molecule with a polar bond isn't necessarily polar, because if bonds are arranged symmetrically around the center, then the partial charge will be the same on each side of the molecule. Such a molecule isn't polar. So, for example, another example to demonstrate this is a tetrachloromethane, which is CCl4. I'll go through this part here. What I mean by this, right, is that in this example, this is polar because there's a clear charge separation. It's an unevenly distributed, right? Actually, I can make this larger. Let me make this larger so it's even more clear, right? Cl. CO, right? This is relatively like here, there. I wouldn't go as that far, but I'd say probably like a there, right? But as you see here, they're equally getting pulled. They're equally getting pulled, but with so that's so they're not equally getting pulled. So here it's getting equally pulled. Here's getting equally pulled. Here's getting equally pulled as on one side, but here it's not the same. It's not the same as the other bonds. It's a clear charge separation. However, with chloroform, so this is considered to be a polar molecule. However, with chloroform, so with a tetrachloromethane, right? This is no longer a polar molecule because the electrons are being equally pulled by the same amount on each side. So that the bond is the polar bonds are equally distributed. The polar bonds are equally distributed amongst each side, and therefore this is no longer a polar molecule because it's equally being distributed on each side. It's the same. So I wouldn't say there's a charge. There's a difference in it's the same bond each time. There's no charge separation within bonds. There's no polar bond because because each bond is exactly the same. There's no difference in electronegativity between each type of bond, right? It's the same type of bond. Therefore, this is no longer considered to be a polar molecule. All right. And the last thing I wanted to point out is that across a period, electronegativity increased. So let's go back to. Yeah, I'll read this out first. So across a period, electronegativity would increase because the nuclear charge is increasing for the same electron shell. So electron shielding is relatively the same as nuclear charge increases. So electrostatic attraction between the nucleus of the atom and the electron pair increases. If you didn't get that part, I'll explain it in a way you can understand, right? So let's say group period 3, right? I could pick it for other examples. It's the exact same principle anyway, but I'll pick period 3. The electronegativity, as you see here, is always increasing, right? The reason for that is, you can clearly see here the electronegativity is always increasing. Why is that? It's because the nuclear charge as you're going across the period, the nuclear charge would increase. As remember, for the nuclear charge is increasing as you're going across the period. At the same time, this increasing, but then the electron shell isn't increasing. You're not adding electrons to another energy level. The electrons are all on the same energy level. Therefore, the electron shielding is the same. The distance between the nucleus and outermost electrons are the same. So it's pretty much having a higher nuclear charge for the same electron shielding and the same distance, so the same attraction. So that's what's causing the size of these atoms to decrease, because the nuclear charge is much more strongly felt. Therefore, as you go across the period, electronegativity would increase because there's a stronger electrostatic attraction between the nucleus of the atom and an outermost electron or an electron pair. So it would have a stronger if there's an electron pair, as you go across the period, the atoms would have a stronger electrostatic attraction between the nucleus and the outermost electron because the nuclear charge is higher, electron shielding is relatively the same or more weakly felt. So yeah, as you go across the period, electronegativity would increase because there's a higher nuclear charge and therefore higher electrostatic attraction between the nucleus and and an electron pair. And that is it, I believe. Yeah, it's the same. Remember, same energy level. These electrons are being added to the same energy level, and that's it.